So now it is time to do an example. Somebody hands you this robot, and we want to apply all of our steps and see where we go. Step one is we need to label all the axes. My axes, these are revolute. So these axes have to be right on these joints that are revolving. This one is straight out of the page. That's going to be Z0. Right over here is Z1. And then somebody's handily given me the final frame. This is going to be Z2 coming out of the frame there. Now we have to establish the base frame. This is step 2, and we can put the origin anywhere on this Z0 axis. But since these are all in the plane, it makes sense to put it in the plane. I can again have it any direction. I'm going to have it coming right out this side, X0, which means that Y0, to make a right-handed frame, we're going to have that come right out here, Y0. So now I'm going to be in my loop from I equals 1 to n minus 1. So I've got 2, so I've only got one step in this loop. So first we've got to locate the origin where the common normal to Zi and Zi minus 1 intersects Zi. So if we look at this from the side, if I've got my links here, and I've got this is going to be my Z0, and right here is my Z1, and my Z2. I can have any number of common normals. I could have a common normal that's here. I could have a common normal that's here. I could have it anywhere along this joint, and I can pick that conveniently now. That's a degree of freedom that I have. But I'm going to place that normal, since these are parallel. I've got to pick a point for that. And so let's pick a point that's going to be in line with my final X2 axis. So I'm going to put it at the same height as all these other ones. So there's going to be my origin, call that O1, and then I've got to make sure that I take a line that goes between these axes, and that is going to be my direction of my X1. So remember, it comes from the previous one, comes to this intersection point, and extends outwards. And then to make a right-handed frame, I'm going to have my Y1 come out this way. And then you'll notice that this X2 that I have here is coming right through here. So from this Z-axis to this Z-axis, and so that follows my right-handed rule. So it's coming right through here. So this is my origin, O2. And so now I can write in my DH parameters, because somebody's conveniently already given me my final frame here. So I've got 2 links, 1 and 2. My Ri is my distance along my X1 axis from Z0 to Z1. So that's going to be my R1 distance from here to here. Then my alpha I is my twist between my 2 Z-axes, but since these 2 axes are parallel, I have no twist. My D is my offset, and so if I had picked a different spot anywhere along here for my origin, then I could have a non-zero D, but I picked everything so that I want. I've got a 0 there, and then my theta is going to be my revolution here. So that's my theta 1 star. Then my second frame, my distance between my Z-axes along my X2 axis, that distance here is R2. So I've got my R2 there. Since my Z-axes are parallel, I've got no twist. Since I picked my origin, I have no DI. And then my angle that I'm revolving here is my theta 2. And that's a star, because that can change. And what I need to do next is to build my rotation frames. I've got my A1. And we've already worked out what this matrix is, so we can just copy in our values directly. So we got cosine 1, sine 1, that's negative, sine 1, cosine 1, 0, 0, 1, 0, 0. The bottom row is 0, 0, 0, 1. And then we've got our R1, C1, and an R1, S1, and a 0. That's my first frame. My A2 frame is going to be very similar to that, only it's a C2 negative sine 2 and a sine 1 cosine, sine 2 cosine 2, and a 0, 0, 1, 0, 0. And again, I've got my cosine 2 R2 and my sine 2 R2, 0, and a 0, 0, 0, 1. And then my tool frame is going to be expressed as T2. In the base frame, it's going to be multiplying these two together. So my first row here, I'll multiply that through here, and I get C1, C2, and then Then finally plus R1, C1. Multiplying out the next line. Then my third line, finally an easy one. And then another easy one. Now, one of the things you'll notice is that we can do some impressive simplification. So this term over here is our summation identities. And so we can write this as just C1, 2. This term right over here is just going to be the sum, sine 1, 2. And so C1, 2 is equal to the cosine of theta 1 plus theta 2. A handy transformation because these transformation matrices are going to become very large. This one right here becomes negative sine 1, 2. This term here becomes C1, 2. And even these ones simplify down. So this term right here is just R2, S1, 2. And this term right here becomes R2 cosine of 1 plus 2. The easiest way to represent this two-link robot is just to make the first link down to 0. So let's bring that to 0, 0, and then we'll set our rotation to 0 as well. And then we rotate this, and we've got our two-link robot. And so the radial distance, this is a parameter, but it's set here for this one. And then our joint that we can move as we rotate, if I set this to 0, then you can see that my x-axis is aligned. As I increase that, similarly for my next joint, it's got some radial distance that it offsets to the end effector. Everything else is 0 except my revolute joint. And so if I set this revolute joint to 0, they're aligned. Then as I increase that, it rotates around that point. Here's our 3-joint manipulator. And so remember, our first step is to put in the z-axes. So Z0, Z1, Z2. We're going to make them all coming out of the page. If we were to look at that, 1, 2, 3 is my axes. I've got Z0, Z1, Z2, and then if you know this is a right-hand frame, we've got our Z3 coming out of here. Z3. So these are all going to be parallel. So again, I can place my origins anywhere I want, but let's make this convenient for ourselves. And so we've already got X3 coming out here. It would be nice if we picked everybody so that they're all in the same plane, and then we have no D offsets. So you'll notice that this D value that I'm picking right here is going to be in the air. It's not actually inside the joint, and that's okay because we're only worried about what is the total transformation between these two frames. So I'm going to set my base frame in the air. It's not even inside the robot. That's okay because that's going to simplify my DH table. In fact, I can go in here and say they're all going to be zeros. So let's build this out. I've got to set my base frame. Again, I'll pick it conveniently. So I've got my X0 there, coming through there. I've got my origins that I'm going to place on each of these points the same heights. And so then my Z1 axis has to intersect both Z1 and Z0. Since they are parallel, then I can pick it at any height, but I've picked my points here. And so if I go from here, I dot line until I get to this origin, and then I continue that on. That is my X1. And I start from here, this is Z1 all the way to Z2. And then I continue that on. That is my X2. And then I'd go from here, and I've already been given where my X3 is. So you see it continues on and comes back and intersects. And then I put my Y values to get a right-handed frame. And then I am finished. And so I've got 3 links, 1, 2, 3. For each of these, I've got my radial distance, R1, R2, Then this distance over here is R3. All my z-axes are parallel, so these are going to be zeros. And then all my joints are revolute. So these are theta 1 star, theta 2 star, theta 3 star. And remember, it's going to go from my x-axis to my next axis about my previous z-axis. So here's my theta 2, and here's my theta 3. We're not going to go through the misery of building my frame. It would be T3 in frame 0, which will be just A1 times A2 times A3. The 3-link robot just has a non-zero axis here. This is our 3-joint robot. It's a planar manipulator. We can revolve around each of these joints. We get a larger workspace because of it. Now, in my original drawing, I did have a little bit of an offset for the D values. Let's put in this D offset for each one of them. So from the side, we can appreciate that. And here, since I've got a D offset, if I actually had this robot, I could put that origin of the first frame over here to put everything in line, or not. So let's get rid of these D offsets again, and you can see it going back into its everybody in the same plane form. Sometimes it's nice to put that offset because then you don't have to worry about joint collisions as the robot folds in on itself. You'll see here that the robot is going to crash in itself. And this self-intersection, generally bad form, whereas if I only had a little bit of D offset, then that intersection doesn't happen. So here somebody has given me an RPP robot. Step 1 is put my z-axes in. This is the direction that my first revolute joint is over, so that's going to be z0. My prismatic joint, z1. And I've got my z2. And again, these things can extend in both directions. I can put my values wherever I want to place them. Let's just say that I want to place my origin down here at the base. Then I can pick my x-axis. So this is going to be at my x1 and then my y1. And I've established my base frame. I go and I place my next x-axis. You notice that these z-axes are intersecting. I can place it wherever I want. So I'm going to just place it, right here. My x1 with my origin coming through here, because it's going to be perpendicular to both of these. I have my z1 and my z2 axis, they intersect. And so I've got to pick that intersection point. This is going to be my O2. And I can pick my x-axis, can either be into the page or out of the page. It'll be easier for me to draw it coming out of the page, but that is some freedom that you can do. So this is my x2 coming out of the page. To make a right-handed frame here, my x3 has to come out in this direction. So now I need to look through here and look at my link rotations. So if I drop this guy down here, this angle right here, that's going to be my theta 1, and it's a revolute joint. This distance that goes from here to here, that is going to be my d1, whereas this distance from here to here, that's my variable d2 star. And then remember my twist for my x2 axis, that's going to come from my z1 axis. How much am I twisting around to get to my x2 axis? So that is this total distance over here, 270 degrees, or we can talk about the negative 90 degrees. And then I've got my distance that I'm moving here. That is going to be my d3 star. And so I can write these in. I've got links 1, 2, and 3. I know that this is my theta 1 star, and I've got my d2 star and my d3 star. I have 0 radial offset, and my z-axes are parallel, but I do have a d1 value here. Second link, since they intersect, I've got no radial distance. I do have an alpha twist, which I said was either 270 degrees or negative 90 degrees. I've got my prismatic joint, and then I've got no rotation about my theta, so 0 degrees. Then my final third joint, again, these axes intersect, so I've got 0 here. They're parallel, my z-axes, so there's no change there, and there's no rotation. And so then I've got these, and I can build out my transformation matrices, C1 minus sine 1, and I've got my sine 1, cosine 1, and then 0, 0, 1. 0, 0, and I've got a little offset in my D1. My next frame, my 2 frame, this one has a twist on it, and it's also got a D offset. So I've got my D2 over here. And then if I insert what this twist does, I get a 1, 0, 0, and then a 0, 0, negative 1, and a 0, 1, 0. My A3, it has no change in my rotation, so that's going to be my identity matrix. And it's only got a change in my offset, so that's my D3 star. These are my starred values, and 0, 0. And then I'm going to spare you the excitement of multiplying this out and just tell you that it's cosine 1, sine 1, 0, 0, 0, 0, negative 1, 0, and negative sine 1, cosine 1, 1, and 0. And then I've got my negative S1, D3, my cosine 1, D3, and then my D1 plus D2 and my 1. And you think, well, we might have been able to pull this out directly, because you can see that the total distance my origin has moved in x and y. It's just going to be my D3, which is my extension of my third joint, times my rotation. Whereas my total distance that I move up in z is just D1 plus D2. This is my star value. My x position is given by here. And so that is just going to be that angle that I've rotated around my original axis by my theta 1. My y is going to be just pointed in the opposite direction of my base frame. And then my z is going to be given by my rotation of my base frame. So that gives me my total transformation. So now we've built our third robot. It's got a revolute joint that can revolve around. It's got a prismatic joint that can come up and down. And it's got a second prismatic joint here that can come in and out. So we can look down at the top of that. You can see that prismatic joint as it slides in and as it slides out. My final problem is a 2-joint Cartesian robot. And so I've got to first draw in where my z-axes are. And so my prismatic direction of movement is along here. So I'm going to call that my z1. And then I've got another prismatic joint here. I'm going to call that my Z0. I can locate my base frame anywhere along here. Makes sense to put that origin right at that start. So any distance I move from here is my D value. I'm going to have my X0 come out of the frame, which means that this is going to be my Y0 frame. Now I have to have my point at the intersection, since these two axes intersect here. Since these intersect, then I'm going to have my X1 come out of the frame. It's either coming out of the frame or in. I'm going to have it come out of the frame. Then my Y has to be pointed down this direction. So that's Y1 pointed downwards. Then I've got my Y2 and my Z2 over here, and my origin at the tip of this frame. And I did this because I wanted to place all my Y and my Z in the frame. Now it's time to build our table. So the table, you've got our links. 1 and 2. We've got our Ri, our alpha I, our Di, and our theta I. Our radial offset, since our origins intersect, we'll have a 0 there. Our alpha I is our twist around our X1 to get from our previous Z0. So I had my Z0 to my Z1, that's a negative 90 degrees. Remember, R, it's a total 270 degrees here. So I'll do a negative 90 degrees. My D offset is my D1. That's this. Actually, let's do that in green. This distance here is my D1, whereas this distance here is my D2. Those are variable. So I've got my D1 star. I can write in D2 star here. Theta 1 is how much I revolve to move my two x-axes. But since my two x-axes are parallel, that's a 0. We go to the next one. Again, since these points are along this z-axis, I get 0 there. You notice that my x's align, so I've got 0 twists there. I've got a D2 star distance, and then I have no rotation about my x-axis, so I get a 0 there as well. So now I can build my A matrices. My cosine of 0 is equal to 1. And my sine of 0 is equal to 0. And my cosine of negative 90 degrees is going to be 0. And my sine of negative 90 degrees is equal to negative 1. Cosine of theta is going to be 1. Sine is 0, 0. Now I'm going to be multiplying by my cosine value, which is 0. So I get zeros for my first two terms, and my sine alpha is negative 1. And then I've got a 0, and my cosine negative 1 times a negative 1 gives me a positive 1 and a 0. And then my final term over here, since I've got a 0 and my d1 star. Over here, very similar, only this time there's no rotation. So that simplifies my life a lot. And I just have my 0, 0, d2 star. And so I can multiply these out rather easily. I get a 1, 0, 0, 0. Then I take my next column and multiply that through here. And I get a 0, 0, 1. And then I've got my d1 star here. Then I take my third row and multiply that out there. And I've got a 0, and then my negative 1, 0, and my d2 star. And now let's look at an animation of this joint. And then finally, if we want to have two prismatic joints, well, again, we can just set this distance to 0. We'll set this value to 0, and we have our two-joint Cartesian robot. Have a great day. I look forward to seeing you in class.